And a heart cycle or a cardiac cycle can be considered as the time between the beginning of one heartbeat to the other. And we are interested in the change in length of each of these segments separately compared to the beginning of the cycle. This is what we call strain, the change in length of a shape throughout the time. Today, we're going to introduce the Curie Intelligent Ultrasound project and how we are using deep learning for improving the interpretation of echocardiography data. And we will then introduce our individual projects, as we are 2 of the 6 PhD students working for this project. I'm Müjde. I will start with introducing the project briefly, and then my colleague Christiana will follow after that with her project, and then I will follow after her. So in Marcius, we want to use artificial intelligence technologies to automate the interpretation of echocardiography data from heart patients. We would like to develop and validate a fully automated clinical decision support tool for cardiac abnormalities. And here we have this research hypothesis that there exists currently undiscovered patterns in echocardiography data that is indicative of pathological conditions or poor outcomes. And we can learn them through AI to detect pathological markers and predict risk of poor outcomes. So this figure summarizes the work packages of the project and the interaction between researchers. And ESR here stands for early stage researcher. We are 6 PhD students, ESRs, hosted in 3 different sites. There is University of Maastricht in Netherlands, Catholic University of Leuven in Belgium, and the 2 of us here based at GE and University of Oslo in Norway. So all 6 individual projects are interconnected. We would like to generate virtual patient data and realistic ultrasound simulations based on that. Using these, we want to train custom machine learning algorithms for multiple tasks, such as segmentation and clinical decision making. We would like to also collect real patient data and validate the algorithms in the clinical setup. So my project has the title Deep Learning for Detection of Heart Abnormalities based on anatomical representation of strain. And what is strain is a question that I will hopefully answer very shortly soon. So the focus of my individual research project is to turn the information that we gather through ultrasound scanners into clinical decisions. And we want to do so by using the strain measurements. It's a particular data type that I will explain briefly. So what we see on the left is an image loop from the left ventricle of the heart, one of the chambers of the heart, that is automatically segmented into 6 pieces by the software. Each of the left ventricle segments move and change their shape throughout the cardiac cycle, as we see here. And a heart cycle or a cardiac cycle can be considered as the time between the beginning of one heartbeat to the other. And we are interested in the change in length of each of these segments separately compared to the beginning of the cycle. And this is what we call strain, the change in length of a shape throughout the time. So we have software in GE scanners that the existing software can track this motion and measure the strain, which gives us 1 trace for each segment. And what we see here is actually just 6 of them because we have 6 left ventricle segments on the shape. But this is just one of the views that we use for getting the strain data. And there are in total 3 views, which gives us 18 different time series data, 18 segmental strain curves. So we know that the software works well to track the segments and give us the strain measurements, but we are not sure if we can trust this strain, when we can trust the strain values and how those strain curves can translate into diagnosis. So we would like to develop algorithms, custom machine learning algorithms, several of them, to automatically grade the quality of the strain, to get automated diagnosis, and also quantify the risk and prognosis, the poor outcomes that we were mentioning earlier, and also to validate these algorithms on the clinical data by applying them on real patient data. Another important thing I would like to mention is that this structure we see on the left here, if we take it and rotate it, and we look at it from the top of it, So we, from upside down, we look at it from the top. We end up with this bullseye representation that is shown here. And this is frequently used in the clinics to represent the strain data. It's like a 2D representation of the 3D morphology that we have in this left ventricle of the heart. So that bullseye is actually forming the basis of the data structure that I'm using in my projects. So as I said, strain is naturally a time series data that we gather from 18 different segments of the left ventricle. And I convert them into bullseye and then warp the bullseye into a 2D grid before I can feed it into a neural network. And finally, I apply also padding to this grid so that the information of the neighboring segments are continuously represented in this grid. And it's important to note that we preserve the temporal, we have to preserve the temporal information in this data as well, because you see here, what you see here is just 18 values. This means that we have one value from each of the curves that we see here. So this is like a snapshot within the heart cycle. It's just a single moment in time. But we have the whole heart cycle. So we need to also take care of the temporal strain. And that is why we use the input channels in the neural network as the channels of the input tensor of the strain data before we feed it into neural network. So the spatial dimensions here are for the left ventricle segments, 18 of them, plus the padding. And the temporal dimension, the time axis here, is for the whole heart cycle. So as I said, that was the basis of my strain data pre-processing, as we see on the left here. So what I have in this project is trying to develop a multi-purpose framework for AI strain analysis. There are different tasks that I'm working on, which require a different type of neural network, each of them. So there are 3 tasks. One of them is detecting scar in left ventricle segments locally. So we're interested in whether each of the segment has scar or not. Another model to detect the severity of abnormalities, different abnormalities in the left ventricle of the heart as a whole. This is not local, but as a whole, the whole structure of the left ventricle. Could be left bundle branch block, which is a disease related to the pacing of the electrical signals in the heart, or scar, for example, and also detecting the outcome, the poor outcomes for the patient, such as mortality here. So 3 different tasks that I need to work on, but what we have developed so far is 2 out of 3 for the first 2 that I will mention in the following slide. The first one is the severity classification of abnormalities based on strain. So I started working on a virtual patient data set that was simulated using a tool called CircAdapt. This was a work done by our colleagues at the Maastricht University. So the connection between our work and their work is that the output of their work is the input data for the work that we are doing here. It was a virtual patient data set of 1,000 patients with various degrees of abnormalities in their left ventricle. These abnormalities were related to the contractility, the contraction of the heart as a global for the whole left ventricle, the left ventricle electrical dyssynchrony, and the scars. So here is a quick pipeline, a generic visual to show the flow of the data and the architecture, not in much detail. So as I said, I get the 18 signals, 18 time series data from a patient, from a virtual patient for each of the ventricle segments through the bullseye representation model, which is shown as only a grid structure here. And after the padding, feed it into a neural network. So to predict the severity of different abnormalities. So to go into more details of the architecture, it's actually a simple convolutional neural network with a very shallow architecture of 2 convolutional layers on flattening and then 2 fully connected layers. This neural network was trained simultaneously for all 3 abnormalities of the left ventricle: global contractility, electrical dyssynchrony, and scar. So we see here that this is capable to produce probability values for each of the abnormalities. But it's important to mention that we're not interested in detecting the abnormality itself. So we know for sure that every patient in this data set has the abnormality, but we're interested in how severe is the patient affected by that abnormality. So that's why the probability values correspond to mild, moderate, or severe labels. Our labels are that, not the abnormalities themselves. So that's why I call it multi-class abnormality severity detection. And if you look at the performance, we see that the SCAR and left ventricle electrical dyssynchrony are the ones performing a bit better compared to the global contractility. So this neural network was trained for 100 epochs using an M optimizer, and the training set was actually training and validation set was consisting of 700 plus 200 patients, and the test set had 100 patients. So the results that we see here are the test set with 100 patients in them, and we see that the majority of the patients were accurately classified into the severity of each abnormality. So we see three confusion matrices because of the three abnormalities, but within the confusion matrices, as I emphasized, our labels are differing from mild to severe for labeling to represent the severity of that abnormality. Another study that I was working on was the segmental scar detection for the left ventricle. So this is this time not a global evaluation, but we are interested this time in finding out whether or not each segment in the left ventricle, each of the 18 segments in the left ventricle, are they scarred or not? And again, working on another simulation data set, again, 1,000 virtual patients with scar on their left ventricle segment. So this was specifically generated, again, by our colleagues at Maastricht University, so that we know for sure that these patients have scar or don't have scar at all. So we're interested on detecting scar based on purely left ventricular strain curves. And it's important to mention that, again, we're working with the bullseye representation of the left ventricle, and each of the slices here have their corresponding name depending on the name of the wall in that heart, in that part of the heart. But we are also interested because it's very relevant for the clinics that the doctors would like to know which of the coronary artery territories are affected with scar. So we have three coronary artery territories: left anterior descending, left circumflex, and right coronary artery. And we would like to know also in that level whether or not that artery, that territory has scar. So this is, for example, a sample patient that was in the data set who has scar in their right coronary artery, and just two of the 6 segments within that territory have scar, and the numbers that we see here are actually showing the volume fraction of scar. So we see that around 75% of that, the volume of that segment was scarred, or 16% of that segment was scarred. So in my the neural network architecture I was using this time was a simple, fully convolutional neural network. This is again a very shallow architecture. The data representation is the same, so I'm not going into detail on that part. There were two 2D convolution layers, and there was also a transpose convolution at the end of the neural network. There were 3 convolution layers and 1 transpose convolution. So transpose convolution is what we use to go back to the original dimensions of the input shape, because we are interested in knowing the scar, whether or not a segment has scar for the whole grid that we see here, for the whole bullseye representation. This can be thought of as a segmentation test, for example, like when we are assigning probability values for each of the pixels to belong to a particular object in an image. So it's very similar, but in this case, our image representation is not from a real life picture, but it's from left ventricle segments represented in a bullseye grid. And yeah, that's why I call it detection and localization of scar. So here we're looking at the performance at multiple levels, because first of all, we have the segments. Again, the data set was partitioned into 900 training and validation patients, and 100 patients for the test set. So we see the results from the 100 patients in the test set. And when we look at the segments and look at the no scar and scar predictions, the confusion of them, we actually have a total of 1,800 segments, right? Because we have 100 patients and they all have, each of them has 18 segments. That's why we see here that the numbers add up to 1,800, and we see that majority of the segments were classified correctly. But we also see here that the data set is quite imbalanced simply because of the fact that in a realistic setup, majority of the segments of that patient cannot be scarred. That will be very severe and the patient will not be alive. So in these simulations, the majority, like the ratio of non-scarred segments versus scarred segments were 91. And this was taken into account during training by using a weight matrix in the loss function. I should mention that. And then we move forward to a bit higher level, which is the coronary artery territories. This time, for each patient has each of these territories. So we have 3 different confusion matrices for the territories. And we see that the classification was successful, but we see also that no scar territories were much higher in the number compared to the scar territories. And also, like inter-coronary artery territory, we see that, for example, left circumflex has the least amount of scar and therefore has the least amount of misclassification scar segments. And at the patient level, which is the highest level, which also we thought as an important result to show to the doctors, because when you think about it, they would like to know, first of all, which patient to take more into account, or which patient to consider that they might have scar in their left ventricle segments. So we see that only 3 of the 100 patients were misclassified, and just 97 of them were classified correctly. And another way to look at the results is, of course, using the accuracy values that we see are quite good here at the patient level and coronary artery territories level. And we also looked at the sensitivity and specificity. So sensitivity is, as we know, recall of the positive class, and the positive class that we consider here is the scar class. So recall of scar and recall of no scar is the specificity. If we think about it. And so in sensitivity, we are interested in how well we can identify the patients with scar, and specificity, we are interested in how well we could identify the patients without scar, which looks quite okay. Another way to look at the results is, because we are working with the spatial representation of the strain, we thought it's important to know at each of the levels, the patient level, coronary artery territory level, and the segmental level, what's the accuracy, the class accuracy. So for the scar class, we see that actually for both scar and no scar classes at the patient level, we have very good numbers for the accuracy. And also calculated for each of the coronary artery territories. We see that, for example, left circumflex coronary artery territory, the ones that had no scar were correctly identified, all of them. To read this plot here. On the right side, this is a different information representation here, this rightmost column, because it shows the misclassifications. And this is not related to accuracy, but it's the misclassifications per each of the left ventricle segments. So out of 6 segments that I forgot the name of this particular region, basal something. So this segment had 6 of them had scar and 94 of them had no scar, and 3 out of 6 were misclassified, while 1 out of 94 no scar were misclassified. So that's the way to read this map, and this is one way to show the audience, like the success of localization of them in more detail.